Okay, so let's get started. I'm sure everyone else will filter in. Carly, can you start an attendance sheet if you have I cleaned out my briefcase and I realized I don't have a blank sheet of paper.
I don't think I have a blank sheet.
Thanks. Okay, so the recordings on strengthening will be posted today, and there will be a quick quiz on Carmen that will be due before the class after spring break. Right, so it'll be due. There'll be a Carmen quiz that will be due Monday before class starts. Monday, 10 days from Monday, or 10 days, So there's slightly more than a week to do the quiz, and it should be a quick gimme for 5 points for everybody. Today I want to talk about, we talked about plastic deformation in crystals. Now I'm going to talk about plastic deformation in non-crystalline and semi-crystalline material. And this is a significantly shorter lecture, from the simple reason is that there's a lot we don't know about plasticity in glasses and amorphous metals beyond a lot of very qualitative concepts, but we don't have a lot of really quantitative models. So this is an area that's really, I'd say, ripe for development. Right? We have good engineering models. Like we can put these, into finite element models and get good results. But if we think about the amount of knowledge we have on crystals that comes from the dislocation theory, when you don't have a repeating lattice to be able to describe what the defects are in glass, right? It's not even clear what the fundamental defects are in an amorphous material, what the plasticity carriers are. We have some sort of hand-waving definitions, but nothing really super concrete, right? And also because of that, because we don't have a repeating structure and we don't have easy to move defects, most of the time amorphous materials tend to be very brittle. So we don't get a lot of permanent plastic deformation. We'll see that we see a lot more of a viscoelastic response, which we'll actually be covering in the next lecture on time-dependent mechanical behavior. Right? We'll talk about viscoelastic response and creep. But for right now, we're talking about permanent plastic deformation that can, for the most part, be considered independent of strain rate, or it happens at a time that's of the same order as the application of your stress, right? Not like creep that happens, or viscoelastic response, which happens over a very long period of time. Okay. So, of course, when I say non-crystalline materials, right, we show no long-range order. One thing that really bugs me about all of these pictures is this is a huge exaggeration, right? Right, it's a schematic to show that there's no long-range order. But on average, right, if you are, say, in a glass, right? So here's a silicate glass. By the bonding, you have to have this tetrahedron, right? Right. This is the expected chemical bonding of your local neighborhood. right? So in this glass structure here, all of the atoms are individually happy, right? Because they have the same local configuration. It's the long range and medium range order that breaks down. And the same thing happens in a metallic glass. It's not really like a liquid structure, right? Because even in a liquid, the very local neighborhood is very much the same as the crystal. But, right? So basically, if you have a metallic glass, if you take a metal that normally makes BCC and you cool it down quickly enough, we'll talk about what quickly enough means in a minute, each atom is still in a very close approximation to the BCC structure, right? Because if you deviated too far from that, the atoms wouldn't be happy, right? That's the bonding that they want to make at equilibrium. They're stuck in a metastable state, but it's not like this, perfect rows to this, right? It's more of like a vacancy type structure where atoms are shifted a little bit from their sort of positions, right? So they're not as packed as they should be, but they still have the right number of neighbors for the most part. Right? Of course, we know that above melting temperature, a non-crystalline arrangement is thermodynamically stable. Right? It's a liquid above the melting temperature. Right? On cooling, almost all metals adopt a crystalline conformation below the melting temperature. Right? If we have silicates, though, right, it's once they adopt a network, right, they're stable. Each of these tetrahedrons are currently very happy here. It takes a long time, right, for them to adopt a perfectly regular crystalline structure because it involves making and reforming a whole lot of covalent bonds. All right, so even though it's energetically favorable for them to be here, it kinetically is very difficult. And that's the other frustrating thing when we talk about amorphous materials. We're often talking about metastable structures, right? They're kinetically frustrated structures. They're not at their thermodynamic equilibrium. So that means we can't fall back on some of the thermodynamic arguments that we can make in crystalline materials. Right? So the first metallic glasses, involved cooling rates of 10 to the 6th Kelvin per second, right? To get those, we've now found alloys that can basically be air cooled to metallic glasses. But if we can cool fast enough, we can suppress this crystalline transition, right? So typically, if we have if we cool, when we go from an amorphous state to a crystalline state, we have a volume change, and usually the crystals will be more closely packed than the liquid. But if we cool fast enough, we don't have a volume change, right? And essentially, we have a solid that acts like a supercooled liquid, right? And if we keep cooling, we reach what we would call a glass transition state, right? Where our material has gains a rigidity or a stiffness that is no longer behaves like a liquid, and we compare it to a crystalline solid. So even right off the bat, we're talking in sort of fairly loose terms, right? We can define the glass transition a little more rigorously because in most cases we see a change in the volume versus temperature, right? So we see a change in the thermal expansion coefficient once we reach the glass transition temperature, because it's not easy for vibrational short-range diffusional transformations to occur locally to accommodate right? But the glass transition is not a well-defined temperature, right? It's, the melting temperature is not cooling rate dependent, right? But the glass transition temperature can be, right? If we cool quickly versus cooling slowly, right, we see a glass transition that happens at a different time, and we end up with a different thermal expansion, different volume of our final component. All right. So what does this imply? Right? If it's amorphous, it means we're not ideally packing, right? Obviously, right? Because the ideal packing would be a crystal. So that means if our specific volume is higher than it is as the crystal, that means we have extra space. Each atom has an extra bit that it's taking up relative to either the crystal or sometimes with respect to an ideal amorphous packing, but that concept of ideal amorphous packing is not well defined either, right? But we can call this extra space free volume, right? And I think from a mechanical point of view, free volume is probably the most important concept for describing deformation in glasses and polymers, right? It's sort of the idea that makes all of this make sense, right? Because without sort of that picture in your head, how do atoms move right past each other? How do you get enough? What's your state variable that describes how easy something is to move, right? So if you're in a crystal, right, the dislocation is sort of your key idea. But for amorphous materials, it's going to be free volume, right? And it sort of quantifies the local space available for the displacive flow of molecules, right? So obviously, the higher the free volume, easier our plastic flow is going to be, right? And also, this tells us a couple other things, right? That our mechanical properties are very dependent on the history, right, of our sample. So our complete thermomechanical history is going to affect our properties. Do we think that amorphous materials or crystals are going to exhibit a stronger temperature dependence of plastic properties? Right. It's going to be glasses, right? We have a much stronger temperature dependence over a smaller range than we do for crystals. Right? So we assume here that we're going to have a viscous flow, right? Whereas for elasticity, we said stress was proportional to strain, and the linear proportionality was our elastic stiffness. For viscous flow models, stress is proportional to the strain rate, and our constant of proportionality is viscosity, right? And so to make matters worse, this viscosity isn't always as constant, right? For elasticity, for our elastic stiffness, it didn't matter how fast we loaded it elastically, right? We said the material responds instantaneously. The viscosity is going to be a function of the applied stress or strain rate, depending on how we define viscosity, right? And it may be Newtonian if we're independent of the stress, right? So at very high temperatures, right, things will behave Newtonian. At lower temperatures or lower strain rate, the viscosity is going to be non-Newtonian. What are examples of non-Newtonian fluids? Right? What are the couple basic behaviors for non-Newtonian?
Hard when you have a high strain rate.
They could be shear thickening liquids, right? So cornstarch and water. So whenever you have small particles embedded in a fluid, like as a kid playing in the mud, right? It'll flow, but if you smack the mud, it doesn't, right? So that's a shear thickening. Polymers are shear thickening or the other is shear thinning. Polymers are shear thinning, right? The faster you shear them, the more chain alignment you have, right? You essentially untangle them. Then there's another class. The toothpaste on your toothpaste tends to be, and wall paint. There's a category called Bingham fluids, where you have no shear until you reach a critical shear stress. Then they act like a Newtonian fluid, right? So, think about how easy it is to squeeze the toothpaste out of the tube, but then once it's on your toothbrush, right, and only subject to gravitational forces, it doesn't flow off the toothbrush, right? Paint you want to be able to apply to come off the brush or the roller when it's subject to that shearing force, but you don't want it to run down the wall. Right. So there's a huge number of different non-Newtonian fluid regimes, but they really sort of only apply sort of in the for these materials, we only really think about them in the melt state, which is not useful for mechanical properties, right? So we're not really going to discuss them other than that brief introduction. There was a heading that was sort of lost here, so take a second and just write in shear transformation zone, right? So the idea in a amorphous material is the local unit of plasticity, the carrier of plasticity, is essentially a local rearrangement of a small atomic cluster locally under the influence of a shear. So basically here we see a small region where the free volume is a tiny little bit higher, and under the action of the shear, this atom A jumps from here to here. right? And this allows this cluster to accommodate this shear and gives us small free volume changes elsewhere in our material, right? And because this involves a diffusion-like jump here, that means we have an activation energy, right? So we can use this activation energy concept to develop notions of theories of viscosity in amorphous solids, right? So we have a stress-assisted motion of atoms and the activation of the shear transformation zone, right? We have to overcome an energy barrier, right? Our applied stress is going to bias motion in one direction, right? Just like diffusion down the gradient, right? Our atomic jumps are random if we don't have a concentration gradient, but if we do have a concentration gradient, we have a flux, right? The same way here, our stress is going to bias our atomic motion in the direction that relieves the stress rather than increases the shear stress, right? So if we call the energy decrease this force times a jump distance, right? We can replace force by a shear stress by an area, right? The area on our shear plane, which is equivalent to the slip plane, we can define a activation volume, right? So our shear stress times our area, the area of the plane times our jump distance. This is our activation volume, right? How many atoms, what volume of atoms need to contribute to the motion, right? Then just from kinetics, we can say the net rate of atoms is going to be given by the rate in the difference in the rate between the two directions, right? The one against the stress and the one towards the stress, right? And this here, this V out front, this is our atomic vibration frequency, right? So this is the number of chances we have to make a jump, right? This is the probability of a jump in against the stress and the probability of a jump in the opposite direction, right? In the biased direction. So the net flux is going to be given by this. Yeah.
For against distance, you have to do minus tau Vc, right?
It depends how we do the sign.
I mean, one side is 2 plus, other side is 2 minus.
Right. So how did we define? Right. So this is the energy without the stress. Let me check and make sure I didn't screw it up from Courtney, because I took the equations right from the.
Isn't that just saying that the backwards jump is the initial one plus that little thing at the bottom? So if you go back to the left.
Yeah.
So it's if you're on the right side, then you go back to the left side. You
Yeah.
overcome what's underneath the dotted line and above the dotted line. Right.
That's the logic, but I'm trying to make it work with, right? Because the net. So I need to check and check the book. But basically, the logic is that your activation energy that you need to overcome here is delta U here, going this way, the activation energy is going to be delta U plus the shear stress times the activation volume. But you're asking about yeah, I know, I get what you're asking. I just want to double check. Right, but the simple picture is here, right? And the detail, again, it's not, the detail is not critical. It's just the understanding that there is a bias due to the difference in activation energy. All right, and so we can basically come up with the shear rate by multiplying the flux by the jump distance, dividing by the vertical spacing between the atoms, right? But if we assume isotropy, the jump distance and the vertical spacing are going to be approximately the same, so our shear rate is going to be directly proportional to our flux. And in that case, we can, our viscosity is just basically the inverse, right? It's going to be proportional to the inverse, but the shear stress out front, our jump frequency, and we have a simple thermodynamic derivation for what our viscosity should look like. So and if we have relatively low stresses and high temperatures, right? So meaning that tau divided by kT is much less than 1, right? We end up with a simple Arrhenius form for our viscosity. So at high temperature, the viscosity only depends on our activation energy and the temperature, right? Not the stress. But if we decrease our viscosity is a strong function of our stress, right? And it's a very nonlinear function of our stress. This all, of course, breaks down as T approaches our glass transition temperature, right? So once we're right, then we behave very much like a pure elastic solid, right? So this is really only applicable in the realm between melting and TG, right? We can think about a different free volume model where it's a little more, say, structural as opposed to thermodynamic. And so if we think about the viscous flow, depending on the probability of finding a local region where we have a space to make the atomic jump, right? So that's going to depend very much on the free volume, right? And so here we express the strain rate as the shear rate, the probability of finding a spot to do the jump, and the driving force for the jump, right? We end up with a viscosity that depends on the nominal volume, our ideal volume, minus divided by our deviation from our ideal volume, right? And we introduce temperature by considering the difference in thermal expansion, right? And again, this is sort of a hand-waving argument, right? And so we have a viscosity that depends on the free volume here, right, where our free volume is going to be a function of the difference between the temperature and the glass transition temperature. This is this free volume here is sometimes called the Crest-Cohen free volume, temperature-dependent free volume. But again, the general idea of this is that the probability of finding a space for our atom to jump into is going to be a function of the free volume. And our viscosity then is going to be a function of the free volume. Right. Again, both of these break down as we approach the glass transition, right? So this is inverse temperature, right? And at high temperatures, it works really well. As we approach the glass transition, on both, this breaks down. So this is for two different organic crystals. But notice the range of viscosity here. Right, this is a log scale. This goes -2 to the 13 to 13. So we have 15 orders of magnitude change in viscosity, right? So what does that sort of tell us about the mechanical properties as we go from Tm to Tg, right? If viscosity is our proportionality constant between shear rate and stress, means we have 15 orders of magnitude change in the amount of stress it takes to cause plastic flow over that range, right? That's huge. That's astronomical, right? So by the time our free volume viscosity really starts to break down, we're basically acting like an elastic solid anyway, so we don't need to worry about it too much. But coming up, right, this is sort of one of those grand challenge problems, right? A theory for viscosity that actually explains, that goes from melting all the way to glass transition. And you see that we have a long way to go there, right? We can assume Newtonian behavior at high temperatures for inorganic glasses and metallic glasses. Generally a poor assumption for polymers, right? Polymers, we're always going to have to think about shear thinning behavior, right? Or colloidal type solutions, we're always going to have to think about shear thickening behavior. So if we think about inorganic glasses, our permanent plastic deformation is going to be very highly temperature dependent, right? If we're much higher than the glass transition temperature, right, it behaves purely viscous flow, liquid-like behavior. If we're much lower than our glass transition temperature, we have a perfectly linear elastic solid. In between, where most of the interesting stuff is viscoelasticity, and we'll talk about that coming up, right? So the viscoelastic portion, right? So the total strain is an elastic portion, a viscous portion, and a viscoelastic portion. The elastic portion is due to stretching and distortion of bonds in the glass network. The viscous portion is, as we said, due to the permanent relative displacements of the SiO2 tetrahedron. Right? Remember, we're not actually, when we're distorting this, we're not breaking those covalent bonds. We're rearranging the tetrahedrons, right? And the viscoelasticity is sort of conformal distortions in the network that are time dependent, and if we assume a linear viscoelasticity, that it's permanent, it's perfectly recoverable, right? Not all viscoelastic is completely recoverable, but for linear viscoelastic materials, we say that it is. So if we have a perfect silicate glass, right, we tend to have a significantly higher viscosity than if we put in any kind of glass modifiers, right? So soda lime glass, right, is silicate with Na2O, right, soda and calcium oxide lime, right, and these positive ions interact with the glass network and disrupt our structure. They don't bond into the make covalent bonds with this silicate structure. They sit in the rings, sit in the holes, right, and disrupt the structure, right. And just conceptually, you can see that we're adding a significant free volume to our structure here, right? Of course, now we got the added complication of charge, right? But by increasing the free volume, we have a significant decrease in the viscosity, right? So it's the sort of opposite of crystalline alloys, right? Pure metals are exceptionally weak, right? If you have 5/9 pure copper, right, you can basically pull it by well annealed, you can basically stretch it by hand until you get a significant dislocation content, right? But if you have any kind of alloying elements in there, right, you significantly strengthen. Glasses tend to be the opposite. As soon as you put modifiers in there, you really decrease the viscosity, and it flows, right?
Within the ring, the volume should decrease.
But you break the network, right? You don't have complete connection between the tetrahedrons, right?
So you increase the free volume.
Yeah, you increase the free volume, right? So I mean, I don't have any personal experience glass blowing, right? But from what I understand, talking to people who have, right, making pure quartz laboratory equipment is really, really tricky because it goes from rigid to puddle over a very, very short temperature range, right? Because we've got a really perfectly ordered glass structure, right? You don't have that modifiers in there that give you easier plastic flow at lower temperature. There's a couple arbitrary sort of definitions when you're working with glass. Obviously, the melting point, right? It's sort of a range, right? So melting point is defined when you have a viscosity at 10 to the 2 poise, right? The working point is where the glass is stiff enough that it will roughly keep the shape that you want it to without just completely flowing out, right? It's the upper temperature, right? And that's 10 to the 4th. Softening point is where it becomes too viscous to work easily, right? That's roughly about 10 to the 8th. So the working range is in between the working point and the softening point. The annealing point is the temperature that you need to get above. So it's arbitrarily defined at 10 to the 13th poise. That's the temperature you need to get above to relieve residual stresses in your material, right? Where there's enough energy for thermal fluctuations to reduce any built-up stresses that you have in your glass. And the strain point is the temperature that you sort of have to slow cool below so you're not building up the residual stresses, right? The strain point is sort of this loosely defined term that if you cool it too quickly past that point, the residual stress buildup can cause your piece to shatter, right? It's essentially the point where you stop, where the viscous part of your deformation goes to approximately 0, right? And you only have elastic and brittle behavior, right? And these are just sort of industry-defined terms, right? There's no real physics. It's kind of like saying it's the glass equivalent of the 0.02% strain, yield strain, right? There's no atomic description of that. It just says on the stress strain curve, we draw this. This is about the yield point, and we'll just call that the yield. Define that as the macroscopic yield point of our material, right? These are the same things. We just not arbitrarily, from experience, have just picked viscosity values and defined these terms at these points. Yeah.
Here, for example, for melting point, we do not have an exact point, but what is the range for temperature? All from 200 to...
Yeah, so I mean, just depending on the different types of glass, right? So pure silica, right? So generally, we can say that the melting point gets lower the more stuff you put in it. But I don't know what the actual melting point of actual quartz fused silica crystalline, is. It's high, relatively, right? Not as high as alumina or a lot of ionic ceramics, but significantly higher than most metals and higher than other forms of glass. Metallic glasses tend to be incredibly strong, right? Very high tensile strengths. This is in megapascals. So we have tensile strengths of 3.5, 2 to 3 GPa, right? Which is pretty dang good, right? What's the problem with them? Right? Why don't we use metallic glasses for everything? They're very brittle, right? So pure glass, we'll see we have almost no ductility. We can get ductility, but then we have to put beryllium. It's like the magic thing that makes metallic glass. Gives you a little bit of ductility in metallic glasses, which of course makes it very toxic and expensive to manufacture. Right. So in the 70s, Ashby made these deformation maps. And this basically holds for all glasses, but this is really made for metallic glass. And so what we see is at high temperatures and low stresses, we get homogeneous flow, right? If our stresses are low enough and our temperature is high enough, we have enough mobility that we can activate these shear transformation zones or shear transition zones and get some plastic flow out of there. If we raise the temperature up, we go into a viscoelastic region and then into a fluid region. If we increase our stress, right, this is stress divided by shear modulus. So as our stress approaches higher than our shear modulus value, we enter this completely inhomogeneous flow region. So what happens? Right? We basically, once we're in this regime, once plastic flow starts, our sample breaks. Right? Why? Like what actually happens there? Right? Plastic flow becomes localized and we initiate shear banding, right? So all of our flow becomes localized in a very thin band, right? So for that to happen, we need some kind of auto catalytic behavior. So if we think about if we have a non-Newtonian viscosity that's shear thinning, right? And we trigger a little shear event, right? We have free volume fluctuations, and we trigger the shear event. Some regions are going to shear faster than others, right? Those regions are going to be less viscous, which means for the same stress, they're going to shear more. They'll become even less viscous, right? In reality, our glass isn't strictly shear thinning like that, but we have plastic dissipation, right? So what are we doing? We're generating heat. And the viscosity is a function of temperature, right? So we have regions where our viscosity drops very quickly during the deformation, right? So all of our strain becomes localized to some region. And we have a shear band that immediately, basically on yielding, propagates immediately across our sample. And once we have a shear band that's all the way across our sample, the whole thing this comes apart, right?
So metallic glasses can be conducted very fast, right?
Yes, but still, the conduction is not nearly as fast as right? You're hitting on a controversial area. Okay, so Professor Lewandowski from Case has a couple classic papers where he measured the temperature rise in the shear band and basically said it's a case of adiabatic heating, and the temperature in the shear band went up to approximately the melting temperature, some very high homologous temperature. Recently, there's been some very nice high-resolution DIC with thermal imaging, micro DIC thermal imaging, done by Robert Moss, who's now at I always get it strong, UIUC, right? And they've done measurements that showed temperature rises only on the order of 1 to 10 Kelvin, right? So whether or not it's a thermal effect or something else, or other increased mechanism in free volume, we really don't know. Most people tend to think there's a very significant temperature rise within the shear band, right? But basically, we have a non-Newtonian viscosity, right? And so deformation is an auto-catalytic effect. Shear makes your material softer. And whenever you have something like that, you fail catastrophically, right? So these are some finite element predictions, right? So if we have an initially random sort of free volume fluctuation, and these are pulled, you see very rapidly, shear doesn't happen globally, right? It's not like a crystal, right? Well, I guess it is sort of like a crystal, but it's like a crystal if everything happened on one slip plane, right? Right, but you get shear bands that happen. Why do these happen at relatively a 45-degree angle? It's the direction of maximum shear stress, right? If we're pulling this way, right? Our maximum shear stress is at 45 degrees to this, right? So normal stress is not going to cause significant flow, just like in a crystal, right? We need shear. And these are some little micro pillar experiments with metallic glasses, right? And basically, you see once you start to compress, once it yields, right, you just get shear bands. When you have more complex stress states like indentation with a circular ball, right, you have more complicated shear bands. But notice that the shear bands are not perfectly straight, right? They're curved. The shear bands follow the directions of maximum stress, right? And so when you have a non-uniform stress state, right, you potentially have the shear bands don't necessarily have to be perfectly planar, right? And here we see shear bands in bending. Okay. So that covers it basically for amorphous for glasses, glasses and metallic glasses. In amorphous and semi-crystalline polymers, the picture is generally the same, except our free volume is different, right? Whereas in glasses and metallic glasses, we had the same bonding with respect to direction. In polymers, we have covalent bonding along the chain, but van der Waals, much weaker interaction between the chains, right? So this is the origin of shear thinning behavior, right? If our chains are tangled, right, we have sort of the isotropy of direction of bonding, right? But and it becomes hard to shear. But once our chains are aligned, right, they're much easier to slip past each other, right? And as part of the project problem, we'll sort of actually do a demonstration of that, right? But we actually see a huge change in property over a fairly small temperature range in polymer, right? If we're less than, say, about 0.8 TG, it's perfectly elastic, leads to brittle failure, right? If we're at the TG, we get very extensive cold drawing. If we go to 5% over the TG, we basically have a viscous, purely viscous behavior. So what's happening during this drawing, right, when we're close to the TG? Right, so if we take a dog bone sample, right, have most people see this demonstration in your undergrad, right, where you take a metal and you pull it and you get necking and it fails pretty quickly, and then they take polyethylene dog bone and you pull it and you get a neck that forms and it just keeps stretching and stretching and stretching forever, right? Right, and this is basically what happens is the neck forms. You have the instability. Once the neck forms, you end up getting chain alignment, right? And that this neck region just propagates out, right? So you can think right in this region, we've got some softening happening. Here, we've got chain alignment. We're pulling about along the carbon-carbon bonds. So this is a much stronger region than just outside the neck. Right. So once the neck forms, right, the deformation is going to happen in that region of softening that you have that's just outside the neck, rather than inside where it's significantly stronger. And so you basically can propagate your whole sample like this. And this is sort of the example that you do in the project problems, right? See, you can demonstrate this pretty clearly for yourself if you take, this six pack of beer can or pop bottle, right? And you cut a little segment out of that. You can just pull it by hand, right? And if you pull it slowly, you can draw, a couple inch piece out to a fairly long distance, and it's really strong in the tensile direction. But if you just grab it in the transverse direction, now only you're pulling against these London forces. And you just give it a little tug, and it just falls apart into a bunch of individual strands. It's sort of a fun thing to do. Okay, so we will wrap this up after spring break. Oh, shoot. I just realized I got us a little out of order. So we're going to do this, and then the viscosity, and then we're going to make a little backtrack to twinning and martensite for phase transformations. I meant to do that first, and I just uploaded the lectures out of order. But yeah, so we'll wrap this up. This will be a quick continuation after break. Enjoy TMS, everyone who's going. Come out to the mixer. Michigan is paying this year, so make sure that you drink heavily. And invite your friends.